Okay, so what we're going to be examining now is steady state power. So what we've been doing so far, remember, is we've been examining steady state, but we really have been just looking at steady state voltage and current. So now we're going to look at power. Now, before we look at that, let's just remind ourselves, if we are in DC, just remember here, you'll use capital letters to represent that we're DC. We had power is equal to current times voltage. Well, for AC, we have the same thing for AC, but I'm going to write these in lowercase letters, I times V, and this is, though, something we refer to as the instantaneous power. It is the power at one precise moment in time. Now this presents some interesting things. I don't want to say they're problems, but they're just interesting things that happen. And so to kind of see what interesting things can happen, let's look at an example real quickly here, where we have a voltage, and it's just going to be equal to 120 cosine of 120 pi t volts. Now, if you play around with this a little bit and you just think about the period and when cosine functions are 0, because they're 0 at pi over 2, 3 pi over 2, etc., we can see that at t equals 1 over 240, 3 over 240, 5 over 240, ... that V at t is equal to 0 volts. Well, what's interesting about this, without even looking at what the current is, I don't even need to know that, we know that here that the power would just be 0 times my current, which would be 0 watts. And again, this would be at t equals 1 over 240 times 3 over 240, not times, these are the time places, ... Now, what I think troubles some people at first is that if you imagine this being the voltage coming out of your outlets, you don't think of the fact that, oh, well, I have 0 power at some precise moments in time coming out. Because if you had 0 power, that would indicate, oh, well, wait, your lights wouldn't be on, for instance. And that's the, I don't want to say problem, but that's the issue with looking at instantaneous power. Now, sometimes you need to know instantaneous power, but that's can be sometimes some of the issues with it. So we're going to try and see of a way that we can analyze and look at steady state power, and we're also going to look at something called RMS values, things of that nature, to really get a better handle on how to analyze what the power actually coming from a circuit is. So to do that, what we're going to first start doing here is we're going to look at the fact that I have a voltage. I'm going to write my voltage as just Vm cosine of omega t plus theta v. And then I'll have a current, and I'll just write this as Im cosine of omega t plus theta I. Theta v and theta I are just the phase shifts of the current and voltage. Now, just using some basic graph shifting, horizontal shifts, vertical shifts, kind of things like that. These would be horizontals. Some basic graph shifting, what we could do instead is we could write it, and this is how we're going to write it, is we could write that my voltage is equal to Vm cosine of omega t plus theta v minus theta I, and that the current is equal to, I was about to write Vm again, Im cosine of omega t. Now, I'm not going to take the time to go through and show you why you can do that. It's a pretty easy thing to verify that you can do that. Alright, so what are we going to do here? Well, we're literally just going to sit here and compute the power. So I'm going to write P is equal to, well, it's going to be, I'll go ahead and write the Vm times Im out in front, and then it would be times cosine of omega t plus theta v minus theta I times cosine of omega t. Alright, so what do we do from here? Because we're trying again to get a handle on things, and we really haven't done anything yet. We're still in the same situation we started with, where we would get instantaneous powers being 0. But this is where, again, it's one of the things I always harp on, is the importance of trig identities. The importance of trig identities aren't to like be able to compute, you know, trig functions at various angles or things like that. It's really for things like this, to be able to simplify expressions so that we can get a handle on what's going on here, and actually get some ability to analyze problems. And so the trig identity I'm going to use here is if you have the cosine of alpha times the cosine of beta, that this is equal to 1/2 cosine, I don't really need a parenthesis there, 1/2 cosine of alpha minus beta plus 1/2 cosine of alpha plus beta. Alright, so if we do that, what do we get to do here? Well, we get to write the power then is going to be Vm Im over 2 cosine, well, this would just be cosine now it's alpha minus beta, so we have to be careful here. Let me kind of go back up here and highlight something. This whole quantity is alpha, and this quantity is beta. So I'd have omega t minus omega t, so that would cancel out, and I would just have here on this first one theta v minus theta I. But then I'd have plus Vm Im over 2 cosine. Now I'm going to add these two together. Well, if I add them, I had to get omega t plus omega t, so that would be 2 omega t, and then I still have plus theta v minus theta I. So I've made some progress here, and you might say, how have I made some progress? Well, notice here there is no t associated with this. So, in other words, that's never going to be 0. That term there is never going to be 0. Now, we can't say like, oh, well, that means my power is never going to be 0, my instantaneous power. Your instantaneous power is still going to be 0 at some points, but we have this quantity now here that is not going to be associated with t, so I have something I could analyze dealing with the problem. Now, I also have something weird going on here, where I have both something with t and something with the phase angle. So I'm going to use another trig identity, and the other trig identity I'm going to use here is cosine of alpha plus beta, and then that's equal to cosine of alpha times cosine of beta minus sine of alpha times the sine of beta. And let's go ahead and look what we have here. What we're going to identify is alpha. In this case, we're going to look at 2 omega t being my alpha, and we're going to look at this theta v minus theta I as my beta when we're using this trig identity. So now we're going to get a pretty big equation here. So I'm going to write maybe a little bit smaller. So I have power is equal to Vm Im over 2 cosine of theta v minus theta I plus, well, then I'm going to have Vm Im over 2 cosine, and I'm going to write the theta v minus theta I first, times the cosine of 2 omega t. Yeah. And I still am running out of room because I started writing too big again. So I'll move it down here. Minus Vm Im over 2 sine of theta v minus theta I times the sine of 2 omega t. Well, one thing you could notice here about this nice expression we have here, and we can maybe do a simulation here to kind of verify this, is that it looks like that the frequency of the power, because if I look at this equation here, I mean this term right here would just be a DC offset, is what this term would be, because theta v and theta I are constants. But then I have 2 omega t here and a 2 omega t here for sine. So that looks like I'm doubling the frequency of my voltage and current. So we'll look at a simulation to see if that is indeed the case. So what's the big deal here? What have we accomplished? Doesn't seem like we've accomplished much of anything, but we've actually accomplished quite a bit here. What we have here now is, notice that we have, I'm going to put these boxes in green here. So I've got a term here that's the same, and a term here that's the same, and now I just have a cosine. There's nothing else inside that, it's just a nice cosine of 2 omega t. And then I also have this term right here. So what we can do here is we can rewrite this as P, just pause this a second. Alright, sorry about that. I don't know what happened. I was installing something in the background on my laptop here, which probably was a bad idea, and my screen froze for a second, but we're back. Alright, so where are we at here? Let's just make sure. So we had this 2 green terms that we boxed and this blue term that we boxed, and then what we can do is we're going to write this in a form of that the power is equal to capital P plus capital P cosine of 2 omega t minus Q sine of 2 omega t. Alright, so that's where we're going to actually stop this lesson today. It doesn't seem like we've made a lot of progress, but believe it or not, we've actually made quite a bit of progress here, and we'll see that in the next lesson.